Anything before we get going, guys? How we doing? With YouTube videos, lecture videos, everything good there? Anything else you need? Lab this week, bromination of transtylbene. Starting this week is pretty much becomes full lab. You'll be weighing out your starting material this week. And the lab you're doing this week will be typical of labs you'll be doing from here on out through Organic 2. Okay, let's get going, guys. Somebody needed the thermodynamics handout? Have a look. Okay, transition of halogens to alkenes, typically chlorine or bromine. We went through the mechanism. Importantly, the second halide does not attack a free carbocation. Okay? The second halide attacks a bromonium or chloronium ion, and it attacks and kicks off the other, the back bonded halogen. This is a backside attack. Okay? We covered this on the very important mechanism page. Nucleophile making bonded carbon, backside attack. Not this. How do we know we don't attack a free cation? Well, that's explained on the next page a little bit why. Because of the stereochemistry outcome. We attack the bridge chloronium ion. Which carbon? Because theoretically you could attack either side. We could attack here and kick the chlorine off of that carbon, or we could attack here and kick the chlorine off of that carbon. Well, it comes down to the true structure of this. This is, the chlorine is very electronegative, and it's mad because it's positive. You don't often see a positive halogen. Very much pulling. Will it pull more on? Okay, this is basically pulling, yeah? Will it pull more that way or pull more this way? The answer is it's going to pull more this way and leave this carbon more partial positive. Why? Because it has two rich friends. This carbon can take on more positive. It will allow the chlorine to pull. This carbon over here is like, whoa, you know, you can't take my electrons. Okay, I don't have rich friends. The answer is the same over there. You attack here, it's the same place as if you would have had a cation. That's one reason I like to show the cation, even though it's not actually formed. It helps us think of things. Okay? This is more likely. Okay, predicted products. In terms of just regiochemistry, connecting the bond, no stereochemistry considerations, it's one of the easiest reactions you'll ever do. Bromine adding across the pi bond, you put a bromine on each carbon, right? That's all it is. Boom, boom, boom. Put a bromine here and put a bromine here, right? Huh? What's wrong with that? Oh, somehow I lost a carbon. 4 here, 3 there. No, that's not right. Because when we put a bromine on this carbon, we add a bond to the bromine. Yes, thank you for that. There you go. A bromine on each carbon of the alkene. But then 2 additional things come into play. What was the mechanism for that? I mean, we can just predict and memorize an outcome, but we need to be able to also show a mechanism. Because there's other questions that could go here. For example, when there is stereochemistry, what's the stereochemical outcome? What's the reaction coordinate diagram look like? How many intermediates are here? How many transition states are here? Number of questions that could be asked. In terms of stereochemistry, which we'll look at going further, the only thing you have here is 1 chiral carbon, often indicated with a like a little star. 1 chiral carbon, and this is going to be racemic. We can put that in our notes for now. We'll learn what that means in about another 2 or 3 days. The bond to the bromine will either be forward or back. But hold on, that sounds like a carbocation was involved. There's no carbocation in this reaction, right? Everybody agree? mechanism for that reaction has no carbocation. Right, so sounds like, front back sounds like carbocation. Well, we haven't fully discussed it yet. Okay, just regiochemistry, that's all we need for now. More later. Here, this is not, you don't just add a bromine to each carbon. You don't have, this is an interhalogen. These are rare, but they're possible. You're going to add this across the pi bond, iodine one place, chlorine the other, but where's the iodine going to end up? Which carbon? Well, now we have possibilities. Now we have regiochemistry. There was no regiochemistry up here. There's no choice. I mean, we could switch that bromine for that bromine, but it's the same thing. There's no choice. Is the iodine going to be on the end or the second? End? Why do you say end?
Because the chlorine is more electromagnetic, so the iodine is partial positive.
We have, that's a schizophrenic polarity. Okay? The polarity there has to come from some type of polarization. This is actual polarity, and it's like this, right? Partial minus, partial plus. Which halogen is electrophilic? Iodine. Iodine is going to like electrons because the chlorine is electronegative. These electrons are attracted to which halogen? Electrons are negative. They're attracted to the positive. These electrons attack the positive. Where are we going to leave cation up here? Right or left? Left. Left, correct. So we pull away from the left, attack the iodine, kick off the chlorine. I'll come this way. Boom, boom, boom. Bond to iodine, the cation here, plus Cl minus. And we just made that right there, right? Anything you show as a reaction product has to come from arrows. Okay, what do you think about these cations? Is it actually formed or no? Here's always going to be the answer. Anytime you can back bond, you're going to do that. And it's going to actually happen at the same exact time. That is, at the same exact time this is attacking the iodine, this lone pair is here. There's one transition state. Attacking, as this attacks, this builds up, and it's starting to become partial plus. No, not partial plus, full plus. It's starting to become plus. Becomes plus. Well, as that becomes plus, this starts attracting to it. And again, most books will just show an arrow coming here all at the same time. I think it's too much. I showed this. Now I show this arrow coming in. And that leads to iodine. Now it's back bonded. Two lone pairs. And that iodine is positive. But this guy here is not actually formed. My first two steps happen at the same exact time. This is the first intermediate. This is just me on the board trying to help us along. It's not formed in real life. There you go. Now, this nucleophile, you see, this will form, but it's not that stable. It's strained, three-membered ring. The halogen, which typically is electronegative, is a positive charge. Halogens want to be negative. That thing is not a happy camper. You might ask, well, why did it even form? Why did this even back bond if we don't want to form a three-membered ring and if the iodine doesn't want to become positive? Why did you do that then? Does anybody have an answer for that? Internal bond making is faster, but that still doesn't mean it has to happen. I mean, if it's strained.
Would it be stability?
Do what?
Stability?
Stability?
Yeah, just like more bonds, more stable.
Okay, well you hit on it because I just described instabilities. Strain during a ring is unstable. Charge on iodine is not good. Not good. Anytime we say good, bad, we're talking about stability or energy. No, but you said something there.
It's just the more bonds.
More bonds. We just made a bond, and bonds are good. That's why I did this. This is known to be the intermediate. Now this will attack this because this bond is really strained. It's not a full bond. That iodine is like pulling here. Which bonds are going to pull more on? Top or bottom? Bottom. It's going to pull. It's bonding. I mean, I bonded to you, but I can still pull. It's pulling, leaving this partial plus. Why? Because it has a rich strand. The answer is the same as here. This is the one we're going to eventually attack. There. But we attack backside. We come in here and we kick these electrons off. And now we get our product. Now we can say, hey, boom, boom, boom. The iodine is on the end. He's got his 3 lone pairs back. That one used to be back bonded, but it got kicked off and became a lone pair. And the chlorine bonded where? Well, right here. Now again, back bonding, you might like, well, shouldn't I draw it up? It does not matter yet. Chlorine here. Yeah, it's the same thing. It's also a racemic. We'll, again, learn about that. There's your product. So which carbon is the iodine going to be on? The first one or the second one? No, the iodine's there.
Oh, the first one.
The iodine. Iodine's on the first carbon, right? Right? We see that from our mechanistic knowledge, not from having to memorize anything. But you want to think broader. So when I give you something other than this, you can use the same broad concept and get that answer too. Key point in all these reactions is where are you going to form cation, right or left? Here. And from there it all falls into place. And so this does have regiochemistry. The iodine ends up on the 1 carbon, not the 2 carbon.
Dr. Stevens, just to clarify, we didn't do the mechanism for the bromine reaction above, but it would be the same thing?
We did it for chlorine above, just substituting bromine for chlorine.
Oh, okay.
Okay, this is typically chlorine and bromine. Why not F2? F2 is too reactive. If you do thermodynamic calculations, you'll see it's very exothermic. And you try to react to many organic compounds with fluorine, it'll just go boom. Too much energy coming out, too uncontrolled, too exothermic. Not easy to do. Iodine, on the other hand, is too unreactive, I2. Do those calculations, you'll see reaction of an alkene with I2 is endothermic. And that reaction actually tends to want to reverse. And it ends up not being good. Now you can readily do interhalogens with iodine like we just did. ICL. That reacts very nicely. In lab, we'll be using Br2. Okay, so how do we know it is not a free carbocation? How do we know that we attack a bridged species backside instead? One of the main reasons we know that is from the stereochemical outcome of these reactions. In certain cases, not every reaction has stereochemistry outcomes, but okay. Some it's just not relevant. Here's a case where it's very relevant. If you take cyclohexene and react this alkene with chlorine, you only get this here. You only get trans. The chlorines are only trans. You also get the enantiomer coming later. you do not get the 2-chlorine cis. Trans only. We know that in lab. This is a good old halogenation of an alkene. Our mechanisms always need to also fit stereochemistry outcomes. The mechanism must explain the stereochemistry. It must explain why you get trans and not cis. First off, this reaction I'm showing is stereoselective. Because what's the relationship between trans and cis? Are they constitutional isomers or stereo isomers? Stereo. They're both 1,2-dichlorocyclohexane. So that is trans 1,2, that is cis 1,2. Same name except they have a different stereochemical descriptor, trans or cis. You only get this stereoisomer, not that one. We thus say the reaction is stereoselective for trans. But we will learn there's two types of stereochemistry, diastereomers and enantiomers. Again, this is just for your notes for now. This reaction is diastereoselective, but it's not enantioselective. Because you only get this diastereomer, but you get both enantiomers. Okay, for now though, why do we get trans only and not cis? Well, our mechanism already explains that. Let's look at how it explains it. Okay, pi electrons attack the schizophrenic chlorine. All right, where are you going to leave cation, top or bottom? That's a hole punch. Symmetrical, it doesn't matter. Top or bottom would be the same exact cation. I left it on the top. Attack here, kick that off. We get a new bond to chlorine. By the way, this bond here, this carbon is now tetrahedral. 2 in the plane, 1 forward, 1 back. You can draw the chlorine forward, or you can draw it back. Why do you get both, forward and back? Well, the alkene is planar. Okay? Like this, it's planar. I'll hold it this way. If the chlorine's over here, I attack you, the new bond's going to be forward. If the chlorine's over here, I attack you, the bond's going to be back. There's just a 50-50 chance from the planar face of the alkene. Okay? These carbons are now tetrahedral. Now I'm showing a free cation. We know it's not a free cation, but if it was, how would the chlorine attack the cation? Which side would it attack from? How do you attack cations? Which side? Both sides, 50-50, yes. So if the chlorine attacked this, bond forward, you would end up with chlorine forward and the other one forward, but then you would also should end up with chlorine back and the other one forward. Right? But this should get both cis and trans. But we know that you don't get any cis. So something's not right here, unless you want to say that this chlorine's only going to attack from the back. But that's not right, because a cation is attacked from either side. Maybe it doesn't attack a free carbocation. Same thing over here. If the first bond had been back, and then you attack this from either front or back, you end up with trans and cis, but you don't get cis. The reason is because it's not an attack of a free carbocation. I didn't draw this in here, but what is it really? This doesn't attack here. Instead, what happens? this attacks here. And it attacks at the same exact time, and it's concerted, and we actually get, now if this attacks there, this bond is forward. How's this bond going to be?
Forward.
Forward? Why forward there? I can't hear, guys.
How the chlorine is forward.
Do what?
Chlorine is forward, so we make that bond.
Right, if this hand's forward, and I'm going to make another bond with my thumb to my hand, that bond will also be forward. It can't be. It can't be. How am I going to make a bond from here to here and the bond be over here and be back? It's just physically impossible. If that's forward, this has to be forward. All right? And that's a positive charge. And this is actually what you get. And we know that this is not actually formed. Because, again, it's the same story. All that happens at the same time. Here's your first intermediate. Now the chlorine attacks here. We can still attack the top. Again, it's symmetrical. You can attack either one. Chlorine attacks the top. If we attack here, are we going to attack from the front or back? Why back?
Because it's going to go forward.
Because the bond that's being kicked off is forward. It's like this. Here's that carbon and the chlorine's forward. We're going to come in from the back and kick off that chlorine. These electrons come in here, kick off the chlorine, and what does that give? This bond here is back. When that gets kicked off, it's still forward, and there you go. You get trans, which we know is the only one you get. And so the mechanism that we've been saying for 2 pages and 2 days now explains why we only get trans. Same way over there, you would only get trans. Because if that chlorine back bonded, both bonds would be back and the new chlorine would come in front and you would end up with trans. Up top it says plus enantiomer, is that right? Which one do I show up top? Is the top chlorine back or forward? Back chlorine is forward? Okay, I show this at the top, but then I say plus enantiomer? Is that right?
Yeah.
Okay, well this is the enantiomer. That's the enantiomer. We'll learn how to quickly identify that on forward. You get both of those trans. They are different. So like how your hands are different. One's right, one's left. But they're at the same connectivity. All right? All right, so that's the halogenation of an alkene. Next reaction. Here we're going to react with a halogen, but we're going to include water. When you include water here, you get a trans halohydrin. It will be trans. This example really is not able to illustrate trans, but it does show you how it's a halohydrin. What is that? Halogen, hydra. This is like it's been hydrated, like you're going to have an OH added. Halogen and OH added across the pi bond. Halogen on one carbon, OH on the other. Which carbon is the halogen going to end up on? Right or left? Well, obviously it's right. But why? We need to know why. All right? Alkenes don't react with pure water. First step is alkene reacting with chlorine. Chlorine is your electrophile. Where are we going to leave cation, left or right? On the left. These attack here. We kick off the chlorine. And we get chlorine there. Cation here, right? I mean, that right there tells you the chlorine's going to be out there, right? Cation here. Do you think this is actually formed, or is something going to happen at the same time? This new guy has electrons. Those electrons are coming in here at the same exact time that's going out. It's okay to show it separately, but make sure you say NAF. These back bonds. They're back bonds, and we get chloronium ion. We still have Cl minus around. But we also have water around. And water is actually going to be the nucleophile. It's neutral. Well, that's an anion. We've got some partial plus here. You might think the anion is more attractive. But chlorine likes being an anion. That means it's quite stable. There's other things going on here as well. You could have questions. Both could possibly attack. Usually when you do this, you sort of use excess water. And here in the end, guys, whenever you see halogen and water, the product is a what? Halohydrogen. Okay, you just have, that's on your note card. All right, halogen and water, halohydrogen. Usually you use excess water, and it competes better than that. These electrons attack where? Left or right? Same place as cation would be. We've already said that. It can pull more here. These electrons attack here. How in terms of, see, this, there's really no stereochemistry here we're able to address yet. We've got to learn when is stereochemistry important to consider and when is it not. So that's why I'm not showing any bold dash here. We attack here, kick that off. What does that give? By the way, something else is formed here. Let's make sure we are able to see what else is formed there. That attacks, what does that do? All right, oxygen makes bond. There's one lone pair left. That's a positive charge. And we have, boom, chlorine. Chlorine gets kicked off. We don't magically lose H's. All we did here is lone pair makes bond to carbon. Lone pair make bond to carbon. The H's are still there. We don't just lose them. We've got a product here, but it's not neutral. Can we go neutral? How can we go neutral?
Chlorine can take an H.
We can lose an H from oxygen. We've done that before. What can take the H?
Chlorine.
Yes, this can take the H. Electrons here, what does that give? Electrons there gives this. And it does not matter that I drew the OH up. It's down there, it's up here. It does not matter because the carbon is not chiral. So don't let that worry you. We've got an OH connected to this carbon, right? There it is. I guess final product, right? But what else did we form here? HCl, yes. You see how your mechanism tells you if you formed HCl? You don't have to memorize that, or, I mean, it's just there. Yeah. HCl is a byproduct there, a small molecule byproduct. And we know that this mechanism is going to get the chlorine here, not here. We would not get this. Unless you want to start by putting cation on the right. Now, the reason I like to show cations is because it makes you get the regiochemistry right. If we just did what the book does, I don't see how you tell the difference between getting one of these or the other. You just have to memorize it. Again, that's why I do this. Question?
Would it have been possible for another water molecule to IH?
Yes. Because we're aqueous, how does HCl exist in water? Isn't that how HCl exists in water? If we had used water to take the H, we would have produced that. Right? And that would have just been the end. That's actually more correct, because that's how HCl exists in water. But like I've always told you, I like to reform an actual species. I mean, it's unreasonable to say, in this reaction, HCl is not going to be ionized with water. Of course it will be, yes. We can bring in stereochemistry. When you're doing rings, stereochemistry is more sort of obvious at the beginning. When it's not a ring, it takes a little more information and understanding to deal with the stereochemistry. It's easier to deal with ring stereochemistry, especially here at the outset. So let's do what is this? 1-methyl cyclohexene. Bromine water, what type of product? Halohydrin, or specifically called a bromohydrin. You'll get that product plus an antigen. Okay, where are we going to make cation at? This attacks bromine. Cation top or bottom? Top. So this pulls away from the top and attacks the bromine. Kick that one off. This new bond here, this carbon is now tetrahedral. We can draw it forward or back. Down there I got it back. I'm going to draw it forward here. Cation here, yeah? Have any back bonding potential? Yeah, this is going back bond. This is forward. This is forward. That's plus. The methyl here. How's the methyl going to be here? Methyl will be back. Right? Now tetrahedral. If the bromine's forward, the methyl's got to be back. How's the methyl over here?
Back. Back.
No, here. How's the methyl here?
Pointer.
This is planar. Because that's a cation. It's sp2 trigonal planar. All planar. Okay? Pretend all that's planar. When the bromine comes in and makes the bond, it pushes the methyl back. It makes room and becomes tetrahedral as things spread out more. Okay? There you go. Then what do we have? Water? What does water attack? Top or bottom? The answer's right here. Top right. Got a rich friend. More partial plus can build up here as that bromine pool. Water attacks here. Kicks this off. What is that going to give? We kick it off. The bromine just got kicked off. This bond's still forward. How's the water, how's the OH up here? It's actually water until we lose an H.
It's actually in the front.
The leaving group was forward, so the nucleophile is going to come in back. Oxygen with two H's. That oxygen is now positive. How's the methyl here? How's the methyl? It has to be by default what?
Forward.
Yeah, tetrahedral, twin plane, one back, one forward. The methyl is now forward. We'll talk more about that. Really, test 3. What I don't like to do is just never talk about it and then, okay, let's talk about this now. It's here. And we'll hopefully make test 3 easier, because it'll be like, yeah, we've done that for many weeks now. It's kind of like this. The green is the thing that's going to get kicked off. Okay? Nucleophile comes in here behind the green. Okay, I'm going to throw you the green. All right? Gets kicked off. Coming in, it gets kicked off. But this moves forward to make room for this thing coming in. Kicked off, okay? That's what happens here. The methyl is back, but when the water comes in, it pushes it forward. All right? It's called inversion. This is a result of backside attack. And then we just lose the H. I'm not going to show mechanism for that because we've already done that many times. And here we go. We lose the H. Some people may say minus H plus. Okay? Then that's not a mechanism. I'm just doing that to show you what somebody else may say. And you know the mechanism, right? We did it on the previous. You can lose an H. Okay? You would get what? You would get the bromine forward, the OH back. Oh, hold on. That's bromine back, OH forward. Well, guess what? You really get the enantiomer. What we made is the enantiomer. I did it on purpose so I could show you the enantiomer. How would you get this structure? From the beginning, instead of drawing this back, you would draw that, back, you would draw it, instead of forward, you would draw it back. And if that was back, both of these would be back. And if the bromine was back, how would the water come in? From the front. And if you did it that way, you would end up with that structure. But guess what? You get both. Because at the very beginning, you get both there. And so from then on, you have both. So this has regiochemistry. We know the OH is going to be up here, not down here. It also has stereochemistry. The bromine and OH are always going to be trans. That's why we call it trans-halohydrin. We did call it that, right? What's at the very top? Trans-halohydrin. This reaction does not give a cis-halohydrin. So there's some down here you can do on your own. And next time we may do one or two of these. We'll see how we're doing. Not all those are halohydrins. Looks like the first one is, yeah? Halogen and water. But not all of them are. Question?
With these trans-halohydrin reactions, is there always going to be some type of acid species reformed at the very end? Like with these two examples, one was the HCl and this next one was HBr. So is that always going to be the case, or does it just so happen to work out?
I'd have to think. I mean, I would ask you to just know the mechanism, and you can see if it's going to perform or not. Trust your mechanism. I don't think it's anything to memorize. I'm not going to ask you, does this type of reaction? I could maybe ask you that, but then I wouldn't expect you to just know it from memorization. I would expect you to maybe do mechanism and say, yeah, I do expect it to make HCl.
Well, I guess I was just wondering, like, if you're working through the steps and you see that you're going to make some type of acid, then you can be like, oh, I'm on the right track because I can see that this is eventually going to reform.
Well,
or is that like a bad way to look at it?
I don't know that it's bad. I just have never told a student to look out for that. I don't see where that's useful. Because I do try to stay away from telling you things that is going to promote memorization, because that may help you for a wee little bit, but it's going to hurt you in the long run. So like functional groups. When you react an alkene with a alcohol on your acid catalyst, it's going to make an ether. Yeah, but do you really need to memorize that? I'd rather you think mechanistically and then say, you know what, it is an ether. You know what, we are going to produce acid, and I can do that. Give me a minute to work mechanism. Then I'll answer you. Same thing with math. If someone asks you 58 times 121, you say, give me a minute, let me work that out. And I'll give you an answer in 5 or 10 minutes. And I think that's very reasonable. But again, whatever works for you. Okay. So there we go. All right, we're going along the outline there. What we're under, is it 1 and 2, and then Roman numerals? Where are we at? Then we also have the old Wheel of Fortune here. Transdihalide, transhalohydride we just did. What's next? Epoxides. Yeah. And looks like over here, we're under B. Without a carbocation. B3. Yeah. Addition of oxygen to the alkene using peroxy acids, making epoxides. That's what we're doing here. Now I say oxygen, I'm not talking about elemental oxygen, O2. I'm talking about atomic oxygen. You're adding an oxygen to the alkene, and we're actually making a 3-membered ring, and each carbon is bonded to that oxygen. I might call this an oxidation reaction. It's not typically, the term is not typically used here, but formally it is an oxidation reaction. We make what's called an epoxide. The 3-membered ring with 1 oxygen in there is an epoxide. The more formal IUPAC name is oxirane. Nobody calls it an oxirane. Most people call it epoxide. Most common way to make epoxides are from alkenes and reacting them with this guy. Okay? When we looked at condensed functional group head groups, we showed the CO2H, which was the carboxylic acid. Remember that? We looked at the acid and the aldehyde on that page back then. But this is O3. What is O3? It's an additional oxygen here. And when oxygens are bonded together like that, that's a peroxide. If under my hand was an H, that would be hydrogen peroxide. But it's sort of this acid part. It's called a peroxy acid. Generic, like this. Condensed. One of the most common peroxy acids is MCPBA. Should be in your textbook. Metachloroperoxybenzoic acid. Very commonly known as MCPBA. You can have a variety of these. This is where the R group is the benzene with the metachloro. You can have simple as just R being a methyl group. Mechanism. Again, in terms of making the product, you just connect each carbon to an oxygen and make a three-membered ring. But what's the mechanism and what's in the stereochemistry? Okay, your peroxy acid is polarized, starting with the carbonyl dipole. Pi bond's very polarized, and so it sort of starts it all here. Because of that, these electrons are pulled this way, and these electrons, all these electrons are pulled towards this electron sink here, leaving the terminal oxygen partial positive and electrophilic. Look at the similarities. Bromine, bromine, schizophrenic. We could have O and O and maybe put an H here and an H here. Very similar. These guys over here don't like to bond to each other. They tend to be reactive. Very reactive, dangerous. Very reactive. Usually you use it dilute. You kill microbes on your skin or something. Peroxide, yeah? Okay? Okay for you, bad for microbes. Electrophilic enough for an alkene to react. Not electrophilic enough because it's not as schizophrenic. But if we put a polarizing group over here, now it's peroxy acid. Now this polarization here makes the N one electrophilic enough. And that's what we got here. Where are we going to make cation? Left or right? Left. These attack the oxygen, kick off the other one. Cation here, tertiary cation. This is what got kicked off. It's all right there. You think this is actually formed or no? New group has a long pair. It's going to back bond immediately. It's back bonding right here, okay? But I don't like to use that arrow. Back bonding. What does that give? Gives a three-membered ring. Looks a lot like a bromonium ion. Three-membered ring. The difference is this guy has an H that you can lose and go neutral. You can't go neutral here by losing an H. So here, nucleophile, the only thing that can happen is nucleophile has to attack here and you get a product like that. Here, something can take the H. What can take it? Well, you got this minus. This takes the H. You get a product. Plus that. Again, do you have to memorize that you get that? You just see that you get that from this here. And there you go. You're able to make your final product. Looks a lot like this, but it's neutral. Since it's neutral, we can isolate it. Yes, it is strained. Yes, it's reactive, and we'll look at reactions of epoxides and organic too. But they still can be made and isolated and purified. You see the similarities, though, in the mechanism. Okay? Please focus on your similarities in your mechanism. Anything really new there? Yes, there's nuances, there's particulars that are there, but the general mechanism is the same. Okay, some more below. Need to work stereochemistry into it. The one with ring will be easier for stereochemistry, like I told you at this point. Where are we back here? Wednesday, yeah? Okay, we're getting close to a quiz. Have a quiz at some point. You have nomenclature and you have thermodynamic videos. Okay. Have a good day, guys. Window.